Right now, as you're watching this video, you're hurtling through space at 220 kilometers per second. Not around the sun, that's a different motion at 30 kilometers per second. This is your speed as you orbit around the center of our galaxy, the Milky Way. It's a journey so vast that even at this breakneck speed, it takes our solar system 230 million years to complete just one orbit. The last time we were in this position in the galaxy, dinosaurs hadn't even evolved yet, and that's just one trip around our cosmic neighborhood. The Milky Way galaxy is our cosmic home, a vast island of stars, gas, dust, and dark matter floating in the even vaster ocean of intergalactic space. But just how big is it? The numbers are about to blow your mind, and what's even more incredible is that we've only recently figured out its true scale. Just 10 years ago, our estimates were off by huge amounts. New discoveries from missions like Gaia, the Hubble Space Telescope, and ground-based observatories have revolutionized our understanding of our galaxy's true dimensions. If you're curious about these cosmic mysteries, make sure to subscribe to this channel and give a thumbs up. I am just starting my journey on YouTube, and your support means a lot to me. One quick question: if you could rewrite one law of physics, which one would you change, and how would it transform the universe? Let me know in the comments down below. I will choose the most creative answer. Now let's begin. Let's start with the basics. The Milky Way is a barred spiral galaxy. Imagine a cosmic pinwheel with a bar-shaped structure at its center and spiral arms sweeping outward. From edge to edge, our galaxy spans approximately 100,000 to 120,000 light-years. But recent discoveries suggest it might be even larger, possibly up to 200,000 light-years across, when we include the faint outer regions. To understand what a light-year means, remember that light travels at about 300,000 kilometers per second. In 1 year, light covers nearly 10 trillion kilometers. So when we say the Milky Way is 100,000 light-years across, we're talking about a distance of 1 sextillion kilometers. That's a 1 followed by 21 zeros. By the way, if you want to dive even deeper into the story and secrets of our galaxy, I highly recommend the book called The Milky Way, An Autobiography of Our Galaxy by Moya McTeer. It's a fascinating, up-to-date, and entertaining look at the Milky Way's true size, structure, and cosmic history. The link is in the description and pinned on the comments. But here's what will really mess with your sense of scale. If our solar system was shrunk down to the size of a quarter, a coin you could hold in your hand, the Milky Way would still be larger than the entire United States. Every star would be a microscopic speck of dust, and the distances between them would be measured in meters to kilometers, even at this incredibly shrunken scale. The European Space Agency's Gaia mission has completely transformed our understanding of the Milky Way's structure and size. Launched in 2013, Gaia has measured the precise positions and motions of over 1.8 billion stars. That's only about 1% of the galaxy's total stars, but it's enough to create the most detailed three-dimensional map of our galaxy ever made. What Gaia revealed shocked astronomers. The Milky Way isn't a perfect spiral disk, it's warped like a potato chip, twisted at the edges. This warp extends across the outer 25,000 light-years of the galaxy, with some regions bent up to 5,000 light-years above or below the main disk. Imagine a vinyl record that's been left in the sun and warped. That's our galaxy. But the disk is just one component of our galaxy. The Milky Way also has a massive halo of dark matter extending far beyond the visible stars. This invisible halo might stretch out to 600,000 light-years or more, 5 times the diameter of the visible galaxy. We can't see this dark matter directly, but we can measure its gravitational effects on visible stars and gas clouds. The galactic center, about 26,000 light-years from Earth, harbors a supermassive black hole called Sagittarius A star. This monster has a mass 4 million times greater than our Sun, yet it would fit inside the orbit of Mercury. The 2020 Nobel Prize in Physics was awarded partly for confirming this black hole's existence through decades of observations of stars orbiting around it at speeds up to 7,600 kilometers per second. The Very Large Telescope in Chile has tracked these central stars for over 20 years, watching them whip around the invisible black hole. One star, called S2, completes an orbit in just 16 years, coming within 18 billion kilometers of the black hole. That's about 120 times the Earth-Sun distance. At its closest approach, S2 moves at nearly 3% of the speed of light. Our galaxy contains between 200 and 400 billion stars. The exact number is still debated because we can't see every star, especially those hidden behind dust clouds or on the far side of the galaxy. If you tried to count them at 1 star per second, it would take you over 6,000 years to count them all, and that's just the stars we can theoretically detect. Recent infrared surveys by the Spitzer Space Telescope and WISE, Wide Field Infrared Survey Explorer, have revealed that our previous star counts were probably too low. These telescopes can peer through cosmic dust that blocks visible light, revealing millions of previously hidden stars. Some estimates now suggest the Milky Way might contain up to 1 trillion stars, though most astronomers consider 400 billion more likely. The spiral arms of our galaxy, where most star formation occurs, have poetic names: Perseus, Sagittarius, Scutum Centaurus, and Norma. Our solar system resides in a minor arm called the Orion Spur, positioned between the Perseus and Sagittarius arms. We're about halfway between the galactic center and the visible edge in what astronomers call the Galactic Habitable zone, not too close to the dangerous center, not too far in the lonely outskirts. But here's something that might surprise you. The spiral arms aren't permanent structures, they're density waves like traffic jams in space. Stars and gas clouds move in and out of these arms over millions of years. The arms appear bright because the compression triggers star formation, creating hot, young stars that shine brilliantly before dying out. The mass of our galaxy is even more mind-boggling than its size. The Milky Way contains about 1.5 trillion times the mass of our Sun. But here's the weird part. Only about 60 billion solar masses of that is in stars. Another 60 billion is in gas and dust. The rest, over 90% of our galaxy's mass, is invisible, dark matter. Think about that for a moment. Everything we see, every star, planet, nebula, and dust cloud, represents less than 10% of our galaxy's total mass. We're living in a galaxy dominated by something we can't see, can't touch, and don't fully understand. It's like discovering that your house is actually 10 times larger than you thought, but 90% of it is invisible rooms you can't enter. The rotation of our galaxy reveals this hidden mass. If only visible matter existed, stars at the edge of the galaxy should orbit much slower than those near the center, just like distant planets in our solar system orbit slower than inner planets. But that's not what we see. Stars maintain surprisingly high speeds even at the galaxy's edge, held in place by the gravity of invisible dark matter. The story of how we figured out the Milky Way's true size is almost as incredible as the size itself. For most of human history, we didn't even know galaxies existed. Just 100 years ago, astronomers were still debating whether the Milky Way was the entire universe or just one island among many. The journey from that ignorance to our current detailed maps represents one of humanity's greatest intellectual achievements. The breakthrough came from an unlikely source, a human computer named Henrietta Swan Leavitt. In the early 1900s, she studied photographic plates at Harvard College Observatory, examining stars in the small Magellanic Cloud. She discovered that certain pulsating stars, called Cepheid variables, had a remarkable property. Their pulsation period was directly related to their true brightness. This discovery gave astronomers a cosmic yardstick. By measuring a Cepheid's pulsation period, they could determine its actual brightness. Comparing this to how bright it appeared from Earth revealed its distance. Suddenly, we could measure distances across the galaxy and beyond. Edwin Hubble used Leavitt's discovery to prove that Andromeda was a separate galaxy, instantly expanding the known universe by a factor of thousands. But measuring our own galaxy from the inside is like trying to map a forest while standing among the trees. We can't step outside the Milky Way to get a bird's-eye view. Instead, astronomers have had to be clever, using multiple techniques to piece together our galaxy's structure. Radio astronomy revolutionized our understanding of the Milky Way's shape. In the 1950s, astronomers discovered that hydrogen gas emits radio waves at a specific wavelength, 21 centimeters. This radiation passes through cosmic dust that blocks visible light, allowing us to map gas clouds throughout the galaxy. These observations revealed the spiral structure that we couldn't see with optical telescopes. The Sloan Digital Sky Survey, which began in 2000, has mapped millions of stars in unprecedented detail. By measuring the colors and brightnesses of stars, astronomers can determine their distances and create three-dimensional maps of the galaxy. This survey revealed streams of stars, remnants of smaller galaxies, that the Milky Way has cannibalized over billions of years. One of the most spectacular discoveries is the Sagittarius Stream, a river of stars wrapping around our entire galaxy. This stream is the remains of the Sagittarius dwarf galaxy, which is being torn apart by the Milky Way's gravity. The stream extends over 1 million light-years, making a complete loop around our galaxy. We're literally watching our galaxy eat another galaxy in real time. And if you think the scale of our galaxy is mind-blowing, wait until you zoom out even further. The Milky Way, as enormous as it is just one of over 2 trillion galaxies in the observable universe. To truly appreciate how our galactic home fits into the bigger picture, check out my other video called How Big is the Universe? After learning about the universe's true scale, you'll never look at the night sky the same way again. The link is in the description and on the card above. Now let's continue our journey through our home galaxy. The Gaia mission has taken this mapping to an entirely new level. By measuring tiny shifts in star positions as Earth orbits the Sun, Gaia can determine distances through parallax, the same way your brain judges distance by comparing the views from your 2 eyes. But Gaia's precision is extraordinary. It can measure the width of a human hair from 1,000 kilometers away. Gaia's data has revealed that our galaxy has experienced a turbulent past. About 10 billion years ago, the Milky Way collided with a large dwarf galaxy called Gaia Enceladus. This collision added billions of stars to our galaxy's halo and likely triggered a burst of star formation. The evidence is written in the motions of stars. Millions of them still move together in patterns that reveal their common origin. Even more recently, perhaps 3 billion years ago, another dwarf galaxy passed close to the Milky Way, creating the warp in our galaxy's disk that we observe today. Computer simulations suggest this galaxy, possibly the Sagittarius dwarf, passed through the Milky Way's disk like a stone creating ripples in a pond, but these ripples are made of billions of stars. The thickness of our galaxy's disk varies dramatically. In the inner regions, the disk is about 3,000 light-years thick. But there's also a thin disk of younger stars, only about 1,000 light-years thick, where most current star formation occurs. Our Sun oscillates up and down through this disk as it orbits, completing a vertical cycle every 66 million years. Some scientists have suggested this oscillation might explain mass extinction events on Earth. As we pass through the denser midplane of the disk, we might encounter more cosmic radiation or gravitational perturbations that send comets from the Oort cloud toward the inner solar system. While this idea remains controversial, it shows how our galaxy's structure might directly affect life on Earth. The spiral arms themselves are about 10,000 light-years long and 1,000 light-years wide, though these dimensions vary. They contain about 10% more stars and gas than the regions between them. This might not sound like much, but it's enough to trigger massive star formation, creating the bright blue stars that outline the arms in photographs. Recent observations have revealed that our galaxy is producing new stars at a rate of about 1 to 2 solar masses per year. That might sound slow, but it means the Milky Way creates roughly 7 new stars annually. Some are massive giants that will die in just millions of years, while others are red dwarfs that will shine for trillions of years, far longer than the current age of the universe. The interstellar medium, the space between stars, isn't empty. Each cubic centimeter contains about 1 atom on average, though this varies dramatically. In dense molecular clouds where stars form, the density can reach millions of atoms per cubic centimeter. In the hot bubbles created by supernovae, it drops to less than 0.01 atoms per cubic centimeter. This might sound like nothing, but the galaxy is so vast that the total mass of interstellar gas and dust equals billions of suns. This material is constantly being recycled, incorporated into new stars and planets, then blown back into space when stars die. The calcium in your bones and the iron in your blood have been through this cycle multiple times. The magnetic field of our galaxy is another invisible component that shapes its structure. This field is about 100,000 times weaker than Earth's magnetic field, but it extends across the entire galaxy. It channels cosmic rays, influences star formation, and helps support gas clouds against gravitational collapse. The Planck satellite has mapped this field by observing how it polarizes light from cosmic dust. One of the most exciting recent discoveries is that our galaxy has enormous bubbles extending above and below the galactic disk. The Fermi Gamma Ray Space Telescope revealed these structures, now called Fermi bubbles, which extend 25,000 light-years in each direction. They might be caused by ancient outbursts from our galaxy's central black hole or by intense star formation in the galactic center. Even more recently, the Rosetta X-ray telescope discovered even larger bubbles, extending 45,000 light-years above and below the disk. These structures contain gas heated to millions of degrees, possibly by shock waves from thousands of supernovae. They show that our galaxy is far more dynamic and violent than the peaceful spiral we see in artists' illustrations. The outer regions of our galaxy hold their own surprises. The Apogee survey, which uses infrared spectroscopy to study stellar compositions, has found stars with chemical signatures indicating they formed in completely different galaxies. These immigrant stars are evidence of the Milky Way's cannibalistic past, preserving chemical fossils of galaxies that no longer exist. Our galaxy isn't just a collection of stars scattered randomly through space, it's a complex ecosystem where different populations of stars tell the story of the Milky Way's 13-billion-year history. Like tree rings that record a forest's past, the ages, compositions, and orbits of stars reveal when and how different parts of our galaxy formed. This stellar archaeology has revolutionized our understanding of the Milky Way's true scale and structure. The oldest stars in our galaxy are nearly as old as the universe itself, about 13.6 billion years. These ancient stars formed when the universe contained almost nothing but hydrogen and helium. You can identify them by their lack of heavy elements. Astronomers call them metal-poor stars, though by metals they mean any element heavier than helium. Some of these stars have less than 1/10,000th the iron content of our Sun. Finding these ancient stars is like finding fossils from the universe's childhood. The star SMSS J03130036670839.3, discovered in 2014, has so little iron that astronomers calculate it must have formed from gas, enriched by just a single supernova from one of the universe's first stars. It's a direct link to a time when the Milky Way was just beginning to form. These oldest stars live primarily in the galactic halo, a roughly spherical region extending far beyond the visible disk. They orbit the galaxy on wild, eccentric paths, plunging through the disk at steep angles. Their chaotic orbits tell us they formed before the galaxy settled into its current, organized spiral structure, when the young Milky Way was a turbulent, irregular cloud of gas and dark matter. The globular clusters orbiting our galaxy are spectacular collections of these ancient stars. About 150 of these dense star balls orbit the Milky Way, each containing hundreds of thousands to millions of stars packed into regions just a few dozen light-years across. Omega Centauri, the largest, contains about 10 million stars and might actually be the stripped core of a dwarf galaxy the Milky Way consumed billions of years ago. Recent observations by Hubble have revealed something amazing about these globular clusters. They're not all the same age. Some formed 13 billion years ago, while others are only 10 billion years old. This age spread tells us the young Milky Way experienced multiple waves of star formation, possibly triggered by mergers with other proto-galaxies. The galactic bulge, the football-shaped concentration of stars at our galaxy's center, contains a complex mix of stellar populations. Once thought to be uniformly old, we now know it harbors stars ranging from 13 billion to just a few million years old. The youngest stars orbit close to the central black hole, defying expectations since the extreme gravitational forces that should disrupt star formation. The nuclear star cluster at the very center of our galaxy is one of the densest stellar environments known. Within just a few light-years of the black hole, millions of stars are packed so tightly that if Earth were there, our night sky would shine as bright as twilight from starlight alone. These stars whip around the black hole at incredible speeds, and their orbits have allowed astronomers to measure the black hole's mass with remarkable precision. Moving outward from the center, we encounter the galactic bar, an elongated structure about 27,000 light-years long. This bar rotates like a solid object, completing one rotation every 220 to 230 million years. As it spins, it channels gas toward the center, feeding both star formation and the central black hole. The bar's rotation rate acts like a cosmic clock, influencing when and where spiral arms form. The disk of our galaxy shows a clear age gradient. The thin disk, where our Sun resides, contains stars mostly younger than 10 billion years. The thick disk, which extends about 3,000 light-years above and below the thin disk, contains older stars averaging 11 to 12 billion years old. This structure tells us the galaxy formed from the inside out and from top to bottom, with the thick disk forming first and the thin disk gradually building up over billions of years. Star formation in our galaxy isn't uniform. It happens in waves and bursts. Evidence suggests the Milky Way experienced a massive burst of star formation about 6 billion years ago, possibly triggered by a close encounter with another galaxy. Our Sun formed during the tail end of this burst, 4.6 billion years ago, in a stellar nursery that probably contained thousands of sibling stars now scattered across the galaxy. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, gives us a front-row seat to star formation in action. This stellar nursery, 1,300 light-years away, is creating about 1,000 stars right now. The hottest of these young stars are carving out cavities in the surrounding gas, creating a spectacular cosmic sculpture visible in Hubble images. But the Orion Nebula is small compared to other star-forming regions in our galaxy. The Tarantula Nebula in the Large Magellanic Cloud, technically not part of the Milky Way but close enough to study in detail, is forming stars so rapidly that if it were as close as Orion, it would cast shadows at night. Our own galaxy has regions nearly as impressive, like the Carina Nebula, where stars 50 times more massive than our Sun are being born. These massive stars live fast and die young. A star 50 times the Sun's mass burns through its fuel in just 3 million years, less than 1,000th the Sun's lifetime. When such stars explode as supernovae, they can briefly outshine the entire galaxy, spreading heavy elements across thousands of light years. These explosions are so powerful that they can trigger new waves of star formation by compressing nearby gas clouds. The Cygnus X region, about 4,500 light-years away, is one of the most massive star-forming complexes in our galaxy. It contains enough gas to make several million stars like our Sun and has already formed hundreds of massive stars. Radio observations reveal cavities blown by stellar winds and supernovae, creating a cosmic foam of hot bubbles and dense filaments where new stars continue to form. The spiral arms act as cosmic traffic jams that trigger star formation. As gas clouds orbit the galaxy, they catch up to the slower-moving spiral density waves. The compression triggers gravitational collapse, and millions of years later, new star clusters light up the arms. This is why spiral arms appear blue in galaxy photos. They're outlined by hot, young blue stars that formed recently. But not all of our galaxy's stars formed here. The Milky Way has been capturing and consuming smaller galaxies throughout its history. Right now, several dwarf galaxies are being torn apart by our galaxy's gravity. The Sagittarius dwarf spheroidal galaxy has already been stripped of billions of stars, which now orbit the Milky Way in long streams. The Large and Small Magellanic Clouds, visible from the southern hemisphere, will eventually suffer the same fate. These galactic mergers add not just stars, but also gas and dark matter to our galaxy. Computer simulations suggest the Milky Way has consumed hundreds of smaller galaxies over its lifetime. Each meal adds to our galaxy's mass and can trigger bursts of star formation. Some astronomers think our Sun's birth might have been triggered by one such merger event. When we look at stunning images of the Milky Way, we're seeing only the tip of the cosmic iceberg. The visible stars, gas, and dust that create those beautiful spiral patterns represent less than 10% of our galaxy's total mass. The rest is invisible, mysterious, and completely dominates the structure and behavior of our cosmic home. This is the dark side of the Milky Way, a realm of dark matter, black holes, and invisible forces that shape everything we can see. Dark matter is the elephant in the room when discussing our galaxy's size and mass. We can't see it, we can't touch it, and we don't know what it's made of, but we know it's there because of its gravitational effects. Without dark matter, our galaxy would fly apart. The stars in the outer regions orbit so fast that the gravity of visible matter alone couldn't hold them in place. Something invisible provides the extra gravity needed, about 10 times more than all the visible matter combined. The evidence for dark matter in our galaxy is overwhelming. When astronomers measure how fast stars orbit at different distances from the galactic center, they find something strange. Instead of slowing down with distance like planets in our solar system, stars maintain high speeds even at the galaxy's edge. This flat rotation curve is the smoking gun for dark matter's existence. Vera Rubin's pioneering work in the 1970s first revealed this mystery in other galaxies, and subsequent observations confirmed the same pattern in the Milky Way. Stars 200,000 light-years from the center orbit just as fast as those 50,000 light-years out. It's as if the galaxy is embedded in a massive halo of invisible matter that extends far beyond the visible stars. Recent computer simulations suggest our galaxy's dark matter halo is neither smooth nor symmetrical. It's lumpy, with dense clumps and streams created by the ongoing process of smaller dark matter halos merging with ours. The Gaia satellite has detected subtle effects of these dark matter substructures through their gravitational influence on star streams. One fascinating discovery is that dark matter might not be completely dark. When dark matter particles collide, they might annihilate and produce gamma rays. The Fermi Space Telescope has detected excess gamma rays from the galactic center that some scientists interpret as a dark matter signal. If confirmed, this would be our first direct detection of dark matter particles. But dark matter isn't the only invisible component of our galaxy. Black holes, regions where gravity is so strong that not even light can escape, lurk throughout the Milky Way. We've already mentioned Sagittarius A star, the supermassive black hole at our galaxy's center, but it's far from alone. Our galaxy contains an estimated 100 million stellar mass black holes, the remnants of massive stars that ended their lives in spectacular collapse. These stellar mass black holes are typically 10 to 20 times the mass of our Sun, compressed into regions just dozens of kilometers across. Most drift through space invisibly, detectable only when they have companion stars. The black hole pulls gas from its companion, heating it to millions of degrees before it spirals in. This superheated gas emits X-rays, creating what astronomers call X-ray binaries. The closest known black hole to Earth is V616 Monocerotis, about 3,000 light-years away. That might sound far, but on galactic scales it's practically next door. Statistical models suggest there should be several black holes even closer that we haven't detected yet. There could be a black hole within a few hundred light-years of Earth, drifting silently through space. Recent discoveries have revealed a new class of intermediate mass black holes, weighing hundreds to thousands of times our Sun's mass. These might be the seeds that grow into supermassive black holes, or they could form when stellar mass black holes merge. The globular cluster 47 Tucanae appears to harbor one of these intermediate black holes at its center, detected through its gravitational influence on surrounding stars. The discovery of gravitational waves by LIGO and Virgo has opened a new window into our galaxy's population of black holes. These ripples in space-time, produced when black holes merge, have revealed that stellar mass black holes are more common and more massive than previously thought. Some of the detected mergers involve black holes over 50 times the Sun's mass, challenging our understanding of how such massive black holes form. Neutron stars represent another exotic component of our galaxy. These city-sized remnants of supernova explosions pack more than the Sun's mass into spheres just 20 kilometers across. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. Our galaxy contains an estimated 1 billion neutron stars, most of them ancient and invisible. But some neutron stars are among the most spectacular objects in the galaxy. Pulsars, rapidly spinning neutron stars that emit beams of radiation, act like cosmic lighthouses. The fastest known pulsar in our galaxy, PSR J17482446A, spins 716 times per second. Its surface moves at about 1/4 the speed of light, and its magnetic field is 1 trillion times stronger than Earth's. Magnetars are neutron stars with even more extreme magnetic fields, the strongest known magnetic fields in the universe. These fields are so powerful they would be lethal from 1,000 kilometers away, dissolving your molecular structure. When magnetars experience starquakes, they release more energy in a fraction of a second than our Sun emits in 100,000 years. The interstellar medium between stars isn't truly empty. It's filled with cosmic rays, high-energy particles accelerated to near light speed by supernovae and other violent events. These particles spiral through our galaxy's magnetic field, creating a cosmic ray background that bombards Earth constantly. Some cosmic rays have energies millions of times higher than anything we can produce in particle accelerators. Our galaxy's magnetic field, though weak, plays a crucial role in shaping its structure. This field channels cosmic rays, influences star formation, and helps support gas clouds against gravity. The field is strongest in the spiral arms and has a complex structure with reversals and loops. Recent observations suggest the field might be generated by a galactic dynamo, similar to how Earth generates its magnetic field, but on a scale billions of times larger. Dark energy, the mysterious force causing the universe's expansion to accelerate, also affects our galaxy, though subtly. While dark energy dominates on cosmic scales, pushing galaxy clusters apart, gravity still wins locally. But dark energy sets a fundamental limit on how large gravitationally bound structures can grow. Our local group of galaxies is near this limit, much larger, and dark energy would tear it apart. The Milky Way sits in a cosmic void, a region with fewer galaxies than average. This local void is about 150 million light-years across, and we're near its edge. This positioning affects our galaxy's motion through space and its interactions with neighboring galaxies. We're falling toward the Great Attractor, a gravitational anomaly 150 million light-years away at 600 kilometers per second. Our galaxy might seem eternal and unchanging, but it's actually hurtling toward a cosmic collision that will reshape everything we know about our galactic home. In approximately 4.5 billion years, the Milky Way and Andromeda galaxies will collide in a spectacular cosmic dance that will last billions of years and birth an entirely new galaxy. This isn't speculation, it's a certainty based on precise measurements of Andromeda's motion toward us at 110 kilometers per second. The Hubble Space Telescope and Gaia satellite have tracked the motions of stars in both galaxies with unprecedented precision, confirming that this collision is inevitable. But here's the surprising part. Despite the dramatic name, collision, very few stars will actually collide. The distances between stars are so vast that the two galaxies will pass through each other like ghosts, with their stars simply sliding past one another. Computer simulations show the collision will unfold in slow motion over billions of years. First, the galaxies will make a close pass, their spiral arms stretching and distorting from tidal forces. Streams of stars will be flung into intergalactic space, creating spectacular tails hundreds of thousands of light-years long. Then gravity will pull them back together for a second pass, and possibly a third, before they finally merge into a single elliptical galaxy. During this cosmic ballet, our solar system will likely be flung into a new orbit. We might end up farther from the galactic center, or we could be ejected into one of the tidal tails. There's even a small chance we'll be captured by Andromeda during one of the early passes. But Earth itself, if it still exists after the Sun's evolution, will probably survive unscathed, just with a dramatically different night sky. The collision will trigger a spectacular burst of star formation. As gas clouds from both galaxies collide and compress, millions of new stars will ignite. For a few 100 million years, the merging system will shine as a starburst galaxy, creating stars at 10 to 100 times the current rate. The night sky will blaze with stellar nurseries and young star clusters. but this stellar baby boom will have consequences. The rapid star formation will use up much of the available gas, and the radiation from massive young stars will blow the remaining gas out of the galaxy. Within 1 billion years after the merger, star formation will largely cease. The new galaxy, sometimes called Milkomeda or Milkdromeda, will become a red and dead elliptical galaxy, populated mainly by old red stars. This isn't just speculation about our distant future. We can see galaxy collisions happening throughout the universe right now. The antennae galaxies, 65 million light-years away, show us what the early stages of our collision might look like. The mice galaxies display the long tidal tails we'll develop. And elliptical galaxies throughout the universe represent the end state of such mergers. The local group won't stop with just the Milky Way Andromeda merger. The Triangulum galaxy, the third largest galaxy in our neighborhood, will likely be involved in the collision too. It might merge with us during the initial encounter or orbit the merged galaxy before eventually falling in. The dozens of dwarf galaxies in the local group will be scattered, consumed, or sent flying into intergalactic space. But zoom out even further in time, and an even stranger fate awaits. Dark energy is accelerating the universe's expansion, and this has profound implications for our galaxy's ultimate destiny. Right now, we can see galaxies up to about 46 billion light-years away. But as the universe expands faster and faster, distant galaxies will disappear beyond our cosmic horizon. In about 100 billion years, all galaxies outside our local group will have vanished from view. The merged Milkomeda galaxy will float alone in an apparently empty universe. Future astronomers, if any exist, will see only darkness beyond their galaxy. They'll have no direct evidence of the Big Bang, cosmic expansion, or other galaxies. The universe will have erased its own history. But the story doesn't end there. Even our merged galaxy won't last forever. Stars will continue to age and die, and new star formation will eventually cease entirely as the galaxy runs out of gas. In about 1 trillion years, the last stars will form. These will be tiny red dwarfs glowing dimly for potentially hundreds of trillions of years. As stars die and aren't replaced, the galaxy will slowly fade. White dwarfs will cool to black dwarfs. Neutron stars will spin down and go quiet. Stellar remnants will occasionally collide, creating brief flashes of light in an otherwise dark galaxy. Over unimaginable timescales, 10 to the 19th to 10 to the 20th years, stars will be ejected from the galaxy through gravitational interactions, leaving only the central black hole. Speaking of black holes, they'll outlive everything else. As our galaxy evolves, stellar mass black holes will gradually spiral toward the center through a process called dynamical friction. They'll merge with each other and eventually with the central supermassive black hole. The merger of the Milky Way and Andromeda black holes alone will release gravitational waves detectable across the universe. This central black hole will grow through accretion and mergers until it contains a significant fraction of the galaxy's mass. But even black holes aren't eternal. Through Hawking radiation, they slowly evaporate. A black hole with the mass of our current galactic center would take about 10 to the 100th years to evaporate, a good few years. But eventually even it will explode in a final burst of radiation. These timescales are so vast they challenge comprehension. The current age of the universe, 13.8 billion years, is nothing compared to the trillions, quadrillions, and googles of years in our galaxy's future. We live in the very early days of the universe, a brief moment when stars shine and life is possible. But let's return to nearer-term futures. In just 1 billion years, the Sun will have grown hot enough to boil Earth's oceans, ending life as we know it. Our descendants, if they survive, will need to migrate to other star systems. The collision with Andromeda might actually help, bringing new stars within easier reach and stirring up the galaxy in ways that could aid interstellar travel. The merger might also affect the galactic habitable zone, the region where conditions are suitable for life. Currently, this zone extends from about 20,000 to 30,000 light-years from the galactic center. Too close, and radiation from the dense stellar environment would sterilize planets. Too far, and there aren't enough heavy elements to form rocky planets. The merger could reshape this zone, potentially making new regions suitable for life while destroying others. Recent simulations suggest that about 10% of stars will be ejected during the merger, flung into intergalactic space with any planets they possess. These rogue star systems will drift through the void, isolated from the merged galaxy. If any harbor life, they'll experience the ultimate cosmic loneliness, a single star in an otherwise empty universe. Now that we've explored the vast scales of our galaxy, from its 100,000 light-year disk to its million light-year dark matter halo, from its 400 billion stars to its inevitable collision with Andromeda, let's bring it back home. Where exactly are we in this cosmic metropolis? How does our location shape our existence? And what does our position in the Milky Way mean for life on Earth and our future as a species? Our solar system resides in what might be the galaxy's sweet spot for life. We're located in the Orion Spur, a minor spiral arm between the major Perseus and Sagittarius arms, about 26,000 light-years from the galactic center. This placement is no accident when it comes to our existence. It's far enough from the dangerous galactic center, but close enough to have the heavy elements necessary for rocky planets and life. The galactic center is a violent place. Within the central few thousand light-years, stars are packed so densely that planetary orbits would be unstable. Stellar encounters would disrupt the Oort cloud, sending comets raining into the inner solar system. The radiation environment is harsh, with frequent supernova and intense X-rays from the central black hole's accretion disk. Complex life would struggle to evolve under such constant bombardment. Recent observations by the Fermi Space Telescope have revealed giant bubbles of gamma-ray emission extending 25,000 light-years above and below the galactic center. These Fermi bubbles are evidence of violent outbursts millions of years ago, possibly from the central black hole swallowing a large gas cloud. If our solar system were closer to the center, we might have been sterilized by such events. But we're also not too far out in the galactic boondocks. The outer regions of the galaxy have fewer heavy elements, what astronomers call low metallicity. These regions formed from primordial gas that hadn't been enriched by many generations of supernovae. Without sufficient carbon, oxygen, silicon, and iron, rocky planets like Earth couldn't form. Life as we know it requires these heavy elements for its basic chemistry. Our position between spiral arms is also fortuitous. Spiral arms are regions of active star formation, which means more supernovae. A supernova within 30 light-years could damage Earth's ozone layer, exposing life to deadly radiation. In the spaces between arms, we experience a supernova that close perhaps once every few hundred million years, rare enough for life to recover between events. The Sun's orbit around the galaxy is nearly circular, which is unusual and beneficial. Many stars have elliptical orbits that carry them in and out of spiral arms and up and down through the galactic disk. Our circular orbit keeps us in a relatively stable environment. We do bob up and down through the disk with a period of about 66 million years, but the amplitude is small enough to avoid the most dangerous regions. Some scientists have proposed that this vertical oscillation might correlate with mass extinction events on Earth. When we pass through the dense galactic midplane, we might encounter more dark matter, disturb more comets, or experience more cosmic rays. The evidence is controversial, but it's intriguing that some extinction events seem to follow a roughly 30 million year pattern, half our vertical oscillation period. Our galaxy's magnetic field provides partial shielding from cosmic rays, high-energy particles that can damage DNA and electronics. This galactic magnetic field, combined with the Sun's heliosphere and Earth's magnetosphere, creates a three-layer shield protecting life on our planet. Our position in a relatively quiet part of the galaxy means this shielding is usually sufficient. The local bubble adds another layer to our cosmic address. We're inside a cavity of hot, low-density gas about 300 light-years across, likely carved out by supernovae over the past 10 to 20 million years. This bubble means we experience less absorption of starlight and fewer interactions with interstellar gas. It's like living in a cosmic clearing that gives us a better view of the universe. Recent research has revealed that our solar system entered this local bubble relatively recently, perhaps 3 million years ago. Some scientists speculate this transition might have affected Earth's climate by changing the flux of cosmic rays reaching our atmosphere. It's a reminder that our galactic environment isn't static. We're constantly moving through different regions with different properties. The Sun itself is slightly unusual for our galactic neighborhood. It's more massive and metal-rich than about 90% of nearby stars. This might not be a coincidence. More massive, metal-rich stars are more likely to have planetary systems capable of supporting life. We might exist precisely because our star is somewhat exceptional for this region of the galaxy. Our motion through the galaxy is complex. In addition to orbiting the galactic center at 220 kilometers per second, we're moving toward the constellation Hercules at about 20 kilometers per second relative to nearby stars. The entire local group is falling toward the Great Attractor at 600 kilometers per second, and the Great Attractor region itself is moving toward the Shapley supercluster. We're part of a cosmic flow involving millions of galaxies. This motion has practical implications. As we move through space, we encounter new stars and planetary systems. In about 1.3 million years, the star Gliese 710 will pass within 1 light-year of the Sun, potentially disturbing the Oort cloud. Over longer timescales, such stellar encounters are inevitable and might have influenced the evolution of life on Earth through comet impacts. The Gaia mission has revolutionized our understanding of stellar motions in our neighborhood. By tracking the precise movements of over 1 billion stars, Gaia has revealed stellar streams, groups of stars moving together through space. Some of these streams pass right through our local region, remnants of dissolved star clusters or dwarf galaxies. We're swimming through a sea of stellar fossils. Our knowledge of the galaxy shapes how we search for extraterrestrial intelligence. The SETI Institute focuses on stars in our galactic neighborhood, particularly those in the galactic habitable zone with Sun-like properties. If intelligent life exists elsewhere in the galaxy, it's most likely to be found in regions similar to ours, not too close to the dangerous center, not too far in the metal-poor outskirts. The famous Drake equation, which estimates the number of communicating civilizations in the galaxy, depends critically on galactic factors. The rate of star formation, the fraction of stars with planets, and the likelihood of life all vary with position in the galaxy. Our improving understanding of galactic structure helps refine these estimates, though the uncertainties remain enormous. As we plan for humanity's future beyond Earth, our galactic position influences our options. The nearest stars are still light-years away, but our position in a relatively dense part of the Orion Spur means we have several potentially habitable systems within 50 light-years. Proxima Centauri b, TRAPPIST-1 and other recently discovered exoplanets offer tantalizing targets for future interstellar missions. Standing under a dark sky far from city lights, you can see our galaxy edge on as a glowing band of light stretching from horizon to horizon. This is the view from inside, the combined light of billions of stars too distant to see individually. Every culture throughout history has gazed at this celestial river and wondered about its nature. Now, after centuries of scientific investigation, we finally understand what we're looking at: our cosmic home, a vast spiral galaxy containing hundreds of billions of stars, countless planets and mysteries we're only beginning to unravel. The true scale of the Milky Way should fundamentally change how you see yourself and humanity's place in the universe. When you realize that our entire solar system is just a microscopic speck in a galaxy so vast that light takes 100,000 years to cross it, it's natural to feel insignificant. But here's the profound truth: you are the universe becoming aware of itself. Through billions of years of cosmic evolution, matter has organized itself into beings capable of contemplating their own existence and mapping the very galaxy they inhabit. Think about what had to happen for you to exist in this moment, reading these words, understanding your place in the galaxy. First, the universe had to create the elements that make up your body. The hydrogen in your cells formed in the first minutes after the Big Bang, the carbon in your DNA, the oxygen you breathe, the iron in your blood, all were forged in the nuclear furnaces of dying stars billions of years ago. These atoms have been on an incredible journey through interstellar space, stellar nurseries, and perhaps multiple generations of stars and planets before becoming part of Earth and eventually you. You are literally made of star stuff, but even more remarkably, your star stuff that has evolved the capacity to understand its own origins. When you learn about the Milky Way's structure, you're not studying something separate from yourself. You're the galaxy studying itself. This cosmic self-awareness is, as far as we know, extraordinarily rare and precious. The vastness of our galaxy puts human concerns into perspective without diminishing their importance. Yes, our conflicts and challenges seem tiny compared to the 100 billion star scale of the Milky Way, but we're the only known place in this vast galaxy where matter has become conscious, where the universe ponders its own existence. That makes Earth and human consciousness cosmically significant, regardless of our physical size. Our growing understanding of the galaxy reveals both our cosmic isolation and our deep connections. We're isolated in the sense that the nearest stars are light years away, and we may be the only technological civilization in the galaxy. But we're connected through the atoms we share with every star, planet, and dust cloud. The same physical laws that govern distant stars govern our bodies. We're part of the galaxy's ongoing story, not separate from it. The Milky Way's size and age also remind us that we're witnessing a specific moment in an ongoing cosmic evolution. Our galaxy has already lived through 13 billion years of history. Stellar generations have come and gone, smaller galaxies have been absorbed, spiral arms have formed and reformed. We happen to exist during a particularly interesting chapter when the galaxy is still actively forming stars, still growing through mergers, still evolving. Future generations, if they exist billions of years from now, will see a very different galaxy. They might witness the Andromeda collision, live in the merged elliptical galaxy, or even see the last stars forming. Each era of cosmic history offers unique perspectives and challenges. We're privileged to live in an era when we can still see other galaxies, still detect the cosmic microwave background, still piece together the universe's history. Understanding our galaxy's true scale should inspire both humility and ambition. Humility because we're so small and young compared to the galaxy's vast scales of space and time. But ambition because we've managed to figure out so much despite our limitations. In just a few centuries, we've gone from thinking the Milky Way might be the entire universe to mapping its structure in exquisite detail. The tools we've developed to study our galaxy showcase human ingenuity at its finest. Radio telescopes that can detect whispers of radiation from across the galaxy. Space missions like Gaia that can measure stellar positions with microscopic precision. Supercomputers that can simulate billions of years of galactic evolution. Each advancement builds on previous discoveries, creating an accelerating expansion of knowledge that mirrors the cosmic expansion itself. But perhaps the most important lesson from understanding our galaxy's scale is that we're all in this together. Every human being shares the same cosmic address: Earth, Solar System, Orion Spur, Milky Way Galaxy, Local Group, Virgo Supercluster, Observable Universe. The atoms in your right hand might have come from a different star than the atoms in your left hand, but they've all traveled through the same galaxy to become part of you. This cosmic perspective doesn't diminish the importance of life on Earth, it elevates it. In all our observations of the galaxy, we've found no clear evidence of other life, let alone intelligent life. Earth might be the only place in this vast galaxy where the universe has evolved eyes to see itself, minds to understand itself, and hearts to appreciate the beauty of existence. That makes our planet unspeakably precious and our responsibility to protect it cosmically significant. As you go about your daily life, remember that you're not separate from the cosmos. You're a part of it, made from it, and participating in its ongoing evolution. Every time you look up at the night sky, you're a collection of atoms forged in stars contemplating other collections of atoms forged in stars. You're the universe looking at itself, marveling at its own existence. The Milky Way galaxy, our cosmic home, is vaster than our minds can truly comprehend. 100,000 light-years across, containing hundreds of billions of stars, wrapped in an even larger halo of dark matter. But despite these mind-boggling scales, or perhaps because of them, our existence becomes more remarkable, not less. We are the galaxy's way of knowing itself, tiny in size but cosmic in significance. So the next time you see the Milky Way stretching across a dark sky, remember, you're not just looking at it. You are it, contemplating itself. And in that moment of cosmic self-recognition, the vast scales collapse into intimate connection. The galaxy isn't just out there, it's in here, in every atom of your being. You are a citizen of the Milky Way, and understanding your cosmic home is understanding yourself. The journey to comprehend our galaxy's true scale leads us to a profound realization. Size doesn't determine significance. Yes, we're physically tiny compared to the galaxy, but we're the part that wonders, explores, and seeks to understand. In all the Milky Way's vast expanse, consciousness like ours might be the rarest and most precious phenomenon of all. We are the galaxy's gift to itself, the means by which it can appreciate its own grandeur. If you are still watching, please subscribe to the channel and give a thumbs up. Your support is my biggest motivation to continue this journey on YouTube. And if you enjoyed this video, you are gonna love this other one at the left side of the screen. Is the speed of light really the fastest speed in the universe? In this video, discover the real science behind faster-than-light phenomena, cosmic expansion, quantum entanglement, Cherenkov radiation, wormholes, the loopholes, and much more. See you there.